All right, guys, starting a new section today. Two dependent samples are matched pairs. Still doing mu and means, but they're going to be dependent. Last week we did independent. Now we're starting dependent, where there are pairs that are matched together. There is some relationship between the pairs. With dependent samples, there's some relationship where each value in one sample is actually paired with a corresponding value in another, so they're actually paired together. Because the hypothesis test and confidence interval use the same distribution of standard error, they're equivalent, they give you the same result. So, sometimes the confidence interval gives you a different result. When we're doing matched pairs, they both give you the same result. Consequently, the null hypothesis that the mean difference equals 0, that's going to be our null all the time during this section. It can be tested by determining whether the confidence interval includes 0. So this is going to be our HO. Our null hypothesis is always going to be the mean of the differences. We're going to put a little d is always equal to 0, which means there is no difference in the matched pairs. That's going to be our null. And then we're going to try to usually have a claim whether or not the mean difference is bigger or smaller than 0. All right, this is just an example of what dependent looks like. It says matched pairs of heights of U.S. presidents and heights of their main opponents. Since there's a relationship as a basis for matching the pairs of data, the data consists of dependent samples. They're dependent, and what we would do is we'd say, okay, our null hypothesis would be, that the mean of the differences of the heights of the president and their opponent would be 0. There's no difference, but probably in an experiment or a test, we'd probably try to prove that the president heights were bigger, because that may be one of the reasons they won, just because they were taller. All right, good experimental design. When designing an experiment or planning a study, using dependent samples is better than using independent because they're already paired together. It takes out some of those extraneous variables that could occur when you're just doing random samples of one thing and random samples of another. Dependent, because they're already paired, is a better design of an experiment. Notation, here you got to know these letters as usual. The little d up here is just for the individual difference of each pair. So you take each pair, find the difference between the values of the pair, that's going to give you your d. Mu of d is the mean of all the differences. So you find the differences of each pair, you find the mean of those, that's mu of d. Remember the little bar on top, d bar, was pulled earlier. It was like when we did the proportions, it was pulled, the pooled p, P-O-O-L-E-D. This is the mean value of the differences for the paired sample data, so that's pulled together. Little s is standard deviation of the differences of the paired data, and n is how many pairs there are. N is always sample size. In this case, how many pairs there are. Make sure get that down. What the notation is. Requirements to be able to do this: number 1, they're dependent. Obviously, that's what we're doing. Number 2, they come from SRSs. They come from simple random samples. And because we're doing mu, the number of pairs has to be bigger than 30, or they have to come from a population that's normally distributed or very close to being normal distribution. Here's our test stat. That should be on your sheet that I gave you earlier with all the test stats on there. But remember, it's for matched pairs, and this is what we're going to do. It's a t again, because it's a mu. Almost every time we do mu, it's a t, unless we know the population standard deviation. It's a t. Degrees of freedom still n minus 1. All right, but that's what we're going to go. And these are the same exact notation we had in the last slide. We're going to find p-values. P-values we're going to find on technology, we hope. And the critical values is the same method that we're going to do. The last slide that you saw with the test stat, we're going to use that test stat, compare it to our t critical value. All right, confidence intervals. We are going to work on confidence intervals, and this is how we're going to do them. We're going to say the mean difference in the middle is the pool difference plus the margin of error, minus the margin of error, and pool difference plus the margin of error. And this is how we're going to find the margin of error using that formula right there, which looks very familiar. The standard deviation over the square root of n and the t-crit. Done that a bunch. And don't forget degrees of freedom, still n minus 1. Okay, we're going to look at one example, and we'll be done. Use the sample data below, the same stuff with the presidents, with a sig level of 0.05 to test the claim that for the population of heights of presidents and their main opponents, the differences have a mean greater than 0. So the presidents tend to be taller than their opponents. So here's 5 different presidents and their heights and the heights of their opponents. And you can see down here on the bottom row, we went ahead and found the differences of all those 5. Okay, first make sure we're allowed to do it. They are paired, so that's check. They're randomly selected, that's check. The data points only have 5, so we need to check, make sure it's normal, so I did the QQ plot. Looks good, check. All right. Your HO, your HO is always going to be this right here. It's always going to be the mean of the differences is 0. Our HA, the typo right there, the HA is going to be greater than 0 because we're trying to test the claim, and that's the claim that the president's height is taller than their opponent's height. So we're going to do a hypothesis test and see if it's true. So I found my stuff here. We're using that sig level. I found the pool differences, which is 3.2, and I found the standard deviation using my calculator and got 11.4. And I'll show you those calculator steps tomorrow in class. And then once you find those two things, you can find your test stat. We're always going to assume the mu of the differences is 0, so that's going to be 0 every time. So really, I got to find the pool D. I got to find the standard deviation of the differences and the square root of how many pairs I used, and I got that number. I got 0.628. So I'm going to compare that with the critical value and see if it falls in the region or not. And here it is. The critical value was 2.132. The test stat we just then calculated was 0.628, so it does not fall in the region right there. So that means I'm going to fail to reject the null. Also, if I use technology, I would find out that the p-value is too high. It's 0.282, and because the p is high, I would still fail to reject the null. And here's our conclusion. Because p exceeds 0.05 or because the test stat doesn't fall in the region, we've failed to reject the null. So that means there is not sufficient evidence to support the claim for the population of heights of presidents and their main opponent. The differences have a mean greater than 0, which means there's not a big difference in their heights right here. In other words, presidents appear to be taller than their opponents, especially on average. The other way to do this is by confidence interval. So here's what I did. Because we were using 0.05 and it was one tail, I doubled the 0.05 to 0.10. That left me with a 90% confidence interval. I calculated E using our formula and got 10.8694. I added it to my D-pooled and I subtracted it from my D-pooled, and I got these two numbers. Now the cool thing about that interval is obviously 0's in there, which means the mean of the differences could be 0 or very close to 0, which means there's not a significant difference in their heights. So I would again fail to reject the null. I'm 90% confident that the true mean of the differences are between those two, comparing the president's height and opponent's height. So the interval does contain 0. It's very possible that the mean of the differences is equal to 0, indicating there's no big difference between the heights. All right, so either method works. Same kind of stuff we were doing last week. The only difference now is we're actually matching the pairs and are dependent instead of two completely different things. And we'll work on it tomorrow like we always do. And I'll see you then.